All right. Good afternoon. My name is Ali Kujuri. I'm one of the joint professors at the Department of Electrical Engineering here at the Sonoma State University, and also one of the organizers of this lecture series. I would like to thank Agilent Technologies, who has been sponsoring this lecture series since the start in 2006. This is the 12th lecture in the series for this academic year, and then next year in September the 1st, in fact that's going to be the first Thursday of the month, we are going to have the next lecture in the series. For today, we have an invited speaker, Mr. Scott Pradels, who is the Vice President of Engineering at Cyan Optics. Cyan Optics is in Petaluma and California, and Scott is going to tell you more about it soon. His talk is titled Wave Division Multiplexing Transport Networks. Mr. Scott Pradels is the VP of Engineering at Cyan Networks, where he is responsible for the development of their packet optical transport systems and multi-layer management products. Prior to Cyan, Scott was a staff engineer at Turin Networks, where he led the architecture and design of their Sonnet, SDH, and optical product lines. Scott began his career as a member of the Advanced Research and Development team at AFC, that's the Advanced Fiber Communications, which is now Labs, where he contributed to the design of wireless transport systems and DSL technologies. Scott holds a Bachelor of Science in Electrical Engineering from California State University at Chico. Here is Scott.
Thanks. I'd like to thank Dr. Kujuri for inviting me to speak today. Let's get the presentation started here. So as Dr. Kujuri said, I'm VP of Engineering at Cyan. We're based in Petaluma, and we develop packet optical transport systems. So WDM is a portion of the products that we develop today. These products get used by communication service providers, and they build their networks using our hardware products and then manage those networks using the software that we develop. Okay, so optical transport networks is what we'll start off talking about, not focusing specifically on DWDM to start. So transport really means just to carry a good or a service from one place to another. You can look at these networks as operating very similar to the way that the highway and road systems do in the United States. You have multiple directions, you have on-ramps and off-ramps, you have freeways where you can get between locations in the network quickly. Key features of an optical transport network, probably number one, it needs to be reliable. No one likes when their internet connection or their video connection at home goes down. These networks need to be reliable or customers will complain. They need to be scalable. We all know bandwidth is growing very quickly. Cell phones are using a lot more bandwidth than they used to when they're just making voice calls. Most people are probably watching video through Netflix. It's on demand today instead of broadcast video as it has been in the past. So these networks need to be able to scale very quickly. It needs to be deterministic. When someone's operating the network, when they make a change to it, they need to know that it's going to do what they expect. And that kind of ties into a common parameter of these networks called OAM. It's operations, administration, and maintenance. And this is something that the service provider needs to be able to basically manage the network that they're deploying. So this is a logical diagram of what we call a 2-degree transport node. So networks are made up of lots of nodes that are interconnected by fibers. So if we take a look at this, we basically divided this node up into 4 quadrants. On the top side here, you have the network side, and this is what's interfacing to the fibers that connect the different nodes in the network. On the bottom side here, you have client interfaces. And then down the middle, we drew a line, and we just divided this node into a west side and an east side. So basically, you could think of the top half here as being the freeways, and the bottom side as being on-ramps and off-ramps to that freeway. So the different types of traffic that we'll talk about, first is drop traffic. This is exiting the freeway. You're getting off the off-ramp and connecting a service, whether it's really bandwidth that you're connecting to a client. This is a drop interface. To get back onto the freeway, you take the on-ramp. We'll call that add traffic. And then if you come into this node and you have no reason to stop, and you're just going to continue on, we'll refer to that as express traffic. So it's going to come in from one direction, just continue on through with no reason to stop at this particular node. So the 2-degree defines the number of interfaces you have on this network side in this node. So there are nodes in the network where you have maybe more than 2 connections. Maybe you have a north, east, south, and west connection in that node. That would be considered a 4-degree node. So we talk about the nodal degree as just the number of interfaces you have on that network side of the box. So the simplest network you could build, point to point. Node A, node B, you connect 2 fibers. Most of these interfaces are bidirectional. So one fiber is carrying direct traffic between node A and node B, and another fiber carrying it the opposite direction. So it's kind of an example we use as we go through some of these different topologies. Let's take a company, say their headquarters is located nearby node A in the network, and maybe they have a factory that's located in node B. Simple as it gets, they can get onto the freeway at node A, carry it over to the factory located near node B, and drop the traffic. Pretty simple case, nothing complicated here. Kind of next in terms of complexity, a linear chain. Here you have node A and node D, which would be considered 1-degree nodes because they only have a single network interface. Node B obviously has 2 interfaces. It's a 2-degree node. So we put our headquarters and factory back in here, connect between node A and node B. If this company decided to build a second factory located in the node D area, you can add your traffic here at node A, express through your node B and node C sites, and drop the traffic at node D. So a transport network needs to be pretty flexible. So in the future, you may have the need to create a connection between the 2 factories. So transport network should be flexible and allow that any-to-any connectivity. So you don't see a whole lot of linear chains deployed. Most of the networks that you'll see deployed, this is a really common topology, it'll be a ring. So this is an 8-node ring. All the nodes on the network are 2-degree. So take a look at the same example. Factory down here connected to node G, and the headquarters at node A. We're expressing through node H. And the reason you want to have a ring is because things can go wrong, and fibers can get cut. It's sometimes referred to in the industry as backhoe fade. A lot of the fibers are buried under the ground, and when they're digging up roads or putting in new pipes, a backhoe will cut one of those fibers. You'll see those signs on the side of the road that say, "Don't dig here," or "Call before digging," because there's pipes or fibers in the ground. So when that happens, you want to have a contingency plan. And what that typically is you'll set up a second path that goes the other way around this ring. So node G and node A, when this fiber gets cut and you lose service between these 2 points, you'll want to detect that failure and switch to this backup path. So typical goals for making that switch is to detect the failure within 10 milliseconds of it happening, and then actually make the switch to the backup path 50 milliseconds later. So about 60 milliseconds from the time that the failure actually occurs to switch to the backup path. That has to do with the time it takes to actually drop a telephone call. So if you have a telephone call up and running and the network stays down for more than 50 milliseconds, there's a good chance that that call will drop, and you'll have to start that call up again. So networks typically defined by the geography that they cover. So this is kind of a list of the different classes of networks that are deployed from smallest to the largest. So access maybe covers a couple of neighborhoods in a city. Metro may cover a large city area like San Francisco may be considered a metro network. A regional network may cover a state or even multiple states. Typically you're looking at distances up to 800 kilometers in a regional network. Long haul, you're putting traffic on that network to carry it a long way, maybe multiple states, maybe San Francisco to Chicago type distances. And then submarine is a really specialized area where you're actually taking the traffic across an ocean or across a large sea. So there's different technologies used in each of these areas depending on the complexity of the network. So here's an example of a regional network. This is a snapshot of a planning tool we use at Cyan. These are the type of networks that our customers would be designing and deploying. Each of these boxes is a transport node, like we showed in the first picture there, and the lines represent the fiber connections. You'll see just like the roadway system, the fibers actually usually go along the roads in most cases. Nodes will be placed in cities so that you can get access to the network. In this case, here's Las Vegas, this is Nevada here, Utah there, and then crosses a little bit into New Mexico. You can see it's not a ring, it's not a linear chain, it's a bunch of interconnected nodes, it's more of a mesh. So these can become pretty difficult to manage. That's where the software comes into play. You need software to be able to manage all the connections that may occur in this network and monitor the optical performance. So the distances that we're dealing with typically in a regional network are somewhere between, on the low end, maybe 20 kilometers. A typical long distance for most optical networking is considered 80 kilometers. That's for a single hop between a transmitter and a receiver. You can see here in this case we have one that's 119, and in that case we may have to use some special techniques to be able to enable that link. So yes. Mm-hmm.
When you are talking about the links, you are assuming that there is no, there are some relays, I suppose, right? There are some optical relays, I suppose, right, along the way, or what? Yeah,
so in this case here, this network actually doesn't show any amplifiers, but there is a way to amplify optical signals. If we had a long distance to go, let's say if we had to go from here up to this point and along that path, we didn't have any need to access any of the data. There are no on-ramps and off-ramps in that path. There is the option of just amplifying the signal as you go along. This network doesn't show one. That's one of the things that our software will manage is to decide where those amplification points need to be in the network. So if you're going to transmit along an 800 kilometer span, you're not going to have enough optical power and link budget to hit that distance, and you can deploy optical amplifiers along the way to boost the signal.
How far do you need to have these optical amplifiers?
So it varies. Typically 100 kilometers is kind of the top end. There are some specialty amplifiers that can allow you to get up to 300 kilometers distance before the need for amplification. But there's drawbacks to pushing the signal too far before regenerating it. Okay, so this is kind of the simplest implementation of an optical transceiver. You've got a laser that's going to generate light at a particular wavelength. It's just going to be a continuous stream of light that we're going to deliver to a modulator. And the modulator just acts like a shutter. It's going to turn on and off, allow light to pass through, or shut it off. We're going to drive that modulator with our TX data stream. So this is just a stream of binary ones and zeros that we're going to use as an input to the modulator. That's going to create a change in the optical intensity that's being delivered to the fiber. You're just going to see a stream of ones and zeros. Basically, this is converting the electrical data into a varying optical intensity on the fiber. That'll travel across the fiber, which then it undergoes some amount of loss, and then be received on a photodiode. The photodiode is going to detect the photons, the intensity of the photons, convert that back to electrical data, and we'll recover our signal from there. So go back here. One other thing I wanted to mention is today, most of the interfaces, a typical interface runs at about 10 gigabits per second. There are deployments of 40 gigabit per second and just starting 100 gigabit per second deployments. over the last few years, I think in the early 90s, bit rates were in the 100 megabit per second range. Mid 90s, it got up to 600 megabits. Late 90s, you hit 2.5 gigabits per second was a common rate. So you had kind of this 4x increase in the bit rates between on about a 5-year interval. Every 5 years, you had a 4x increase in the bit rate. We're starting to hit the limits, and it's getting harder to push that much further than 10 gig today. At 40 gig and 100 gig, they're starting to use new modulation techniques. This is NRZ. All we're doing is on-off keying. We're turn the light on, shut the light off. For 40 gig and 100 gig, they're starting to use phase modulation. So QPSK is a common modulation format used for 40 and 100 gig. So we're starting to push the limits of what's possible with a single interface. And that's really where wavelength division multiplexing, or WDM, comes into play. So basically here with a single channel on a fiber, you've got like a single lane of cars. WDM is like adding additional lanes. We're not changing out the fiber, we're just allowing more signals to be multiplexed onto a single fiber. So a very simple WDM system here with 2 channels. Basically I have 2 transmitters, channel 1 and channel 2 here, that are both transmitting at different wavelengths. So each of those lasers is running at a different wavelength. And those will go into a multiplexer. The multiplexer will combine those onto a single fiber that then we can transmit across the fiber, demultiplex it on the far end, and deliver it to a receiver. One of the important things here is that the receivers are broadband. They don't care what wavelength of light is coming in. So this demultiplexer has to isolate the channel for each of those receivers. You need to have a filter there that will isolate the channel that you're not trying to receive in that case. So a couple of units, refresh before we go on. So wavelength and frequency, we'll talk about WDM in both contexts. So wavelength, typically for WDM, we're talking about nanometers. In the frequency range, we're talking in the hundreds of terahertz. Kind of an example, this isn't visible light that we're dealing with in communication networks. We're really dealing with infrared light. In transport systems, 1310 nanometers and 1550 nanometers are typical wavelengths. More visible light, like as an example, Cyan is 485 nanometers. So in terms of frequency, this is up in the 200 terahertz region. And as you guys probably know, it's just related by the speed of light. And wavelengths we're talking about always in a vacuum. We're not talking about the wavelength in any particular medium. So then optical power, quick refresher, we'll use dB to talk about power ratios, so decibels. 0 is a ratio of 1 to 1, minus 20, a ratio of 1/100th of the power. We don't use linear units too much when dealing with optical, just like you don't with RF. We're typically going to use logarithmic units, or dBm. So 0 dBm is equal to 1 milliwatt of power. So for a typical, this is a 10 gigabit per second long reach transmitter. We're looking at about minus 1 dBm worth of power. It's right around a milliwatt worth of power that's going to transmit into the fiber. And then the sensitivity is the minimum amount of power that the receiver needs to be able to recover the data without errors. So in this case, we're down at minus 24 dBm, which is down in the microwatt range in terms of powers that it can receive. Then the difference between these two we'll refer to as the link budget. So if you can transmit at minus 1 and receive down to minus 24, you can just subtract these two, you have a 23 dB link budget for that transceiver. So when you go through the fiber, you can handle up to 23 dBs worth of loss before you start to receive errors on that data. Okay, so transport networks typically use single mode fiber. Single mode means there's only one path for that fiber to propagate through, one path for the signal to propagate through that fiber. Typical wavelengths we use are around 1310 down in this area, and then more commonly 1550 nanometers is a really common area. That's where you have the lowest loss on the fiber. In this case, this is 1550 nanometers. It's about 1/4 of a dB per kilometer of fiber. So as you increase the fiber length, you get more loss. There's a region here that you want to avoid. It's called the water peak. It's where you have hydrogen oxide ions that will absorb the light. There you have 2 dBs per kilometer, so you can't go very far before you're out of power in that case. I guess one other thing I'd note here is that with a 1/4 dB of loss per kilometer up at 1550 nanometers and around a 20 dB link budget, that means you're looking at about an 80 kilometer distance for a transmitter. So you can go up to 80 kilometers without having to do any type of amplification or expecting any bit errors on that signal. Okay, so the simplest implementation for WDM, and the first one that came about, was to take a signal that's running at 1310 nanometers and one that's up at 1550 nanometers and combine them. And that was it. You had 2 channels. So if you're running at 10 gigabits per second per channel, you created a 20 gigabit per second system by using WDM. And you avoided this water peak in the middle. When people needed more bandwidth, kind of the next logical step is to put these channels closer together. So CWDM stands for coarse wavelength division multiplexing. This example, we're using 8 channels. They start at 1470 nanometers and go up to 1610, and they're spaced 20 nanometers apart. So one difference between CWDM and the WDM example we used before is that the lasers that we use in this case have to be right on frequency. They only have 20 nanometers of slop before they'd be interfering with the adjacent channel. So in this case, those lasers have to be well controlled, get up to 8 channels, or assuming 10 gigabit per second per channel, 80 gigabits per second across that single fiber. So there were some advances in fiber types. People were able to reduce some of the manufacturing imperfections that caused that water peak, basically knock that down. That enabled you to get up to 16 channels using CWDM, same spacing as the 8-channel system we used before. But most systems that are deployed today use DWDM. So if we take the same spectrum of wavelength, it's divided up into a bunch of bands. And these are just, someone wrote a standard, said these are the different bands. They gave them names. The one we're most interested in, though, is the C band, which is a conventional band up at 1550 nanometers. So when you move to dense wave division multiplexing, that C band up at 1550, which spans a total of 32 nanometers. So CWDM took 20 nanometers per channel. Now we're talking about a total span of 32 nanometers. With DWDM, we can fit 80 channels in that same 32 nanometer spectrum. So the spacing between these channels is very tight. It's 0.04 nanometer spacing between channels, or 50 gigahertz in frequency between these different channels. This is a lot of bandwidth, especially if you're talking 10 gigabits per second, and this is 800 gigabits per second. There's no reason why you can't move to 40 and 100 gig interfaces on here, so you can be up in the 8 terabit range using dense WDM in the C-band. So there's other reasons why the C-band is important and why we operate in that region other than the low loss, and we'll talk about that in a little bit here. Okay, any questions before we move on? I'll talk about some of the different equipment implementations we have and how these networks are put together. Any other questions before we start there? Right. So transport platform. So this is a picture of the product we build at Cyan. This is our flagship platform. We have several different platforms that we build in just different sizes and form factors. This one's called the Z77. It's a box that mounts in a telecommunication rack. So this would be mounted in a communication service provider's central office. So it's a nondescript building on the side of the road. They'll place these things, and fibers come into that building, and services that go to their customers leave that building. So this box has several slots, and we build boards that plug into those slots that will do the muxing and demuxing of interfaces, that will light the different wavelengths that are going to be used in the network, provide interfaces to the clients, and then general control and provisioning of those services. So first component that we built, so this would be one of the cards that plugs into this into this platform would be a transponder. So what a transponder does is it takes a client interface. So one of the signals that we want to add on to the DWDM network, which we call a gray wave. We really don't care about the wavelength on this side. On the client side, they can give us any wavelength they want. We'll take that, convert it back to an electrical signal, do a little bit of electrical processing on the signal, and then send it to a line-side transceiver. So the line-side transceiver is actually tuned to a specific wavelength that it's going to transmit on the network side. In terms of the electrical processing, we could just do a little bit of cleanup. We can clock and data recovery, get rid of any jitter or distortion that may have occurred on the signal coming from the client side. Or even better, there's a standard called OTN that was developed by the ITU, the International Telecommunication Union. And this is a wrapper, so we take that client signal, which is the payload we're going to transport, and wrap it with some data where we can monitor errors, run some forward error correction, so if we do take errors in the network, it can correct some of those errors, and provide general support for maintaining and monitoring the network. It's also called digital wrapper is what people will call it, because it acts as a wrapper around that payload that we're going to transport. Same thing when it comes in from the DWDM network, we'd strip that off and give them back just the signal that they need. So typically this might be an Ethernet interface on this side. So you give us an Ethernet signal, we'll wrap it up in a container, and then send it across the DWDM network to its destination. So in that case, if we're talking about the transceiver being 10 gigabits per second, the client is using all that bandwidth. A lot of times those client interfaces don't need a full 10 gigabits per second. So we also have devices called mux sponders that will take multiple client transceivers running at lower rates. So you might have 2.5 gigabit interfaces that get multiplexed into a 10 gig signal, or multiple 1 gigabit interfaces that could also be multiplexed. And that multiplexing is done at the electrical level, not at the optical level. So mux sponder will take multiple interfaces, pack them efficiently into a 10 gig trunk side interface and ship it out. So terminal multiplexer. Terminal multiplexer, and this is back to that original picture we looked at. Very simple. It's going to take those two wavelengths, combine them, ship them out on the network. It's one thing you don't have in this case, you don't have that ability to express through the node optically. So there's no express path. This is basically just a start point and end point. Not much else there. Technologies that you can use on these two sides. On the transmit side, you can just use a simple optical combiner. It's kind of glossy, but you could just combine the two optical signals into the fiber. There's other technologies, thin film filters. There's a company in Colorado that's actually in Santa Rosa where a good portion of the world's supply of thin film filters are manufactured. Or array waveguides that provide higher density interfaces. Thin film filters typically are used for like 1 to 8 channels worth of muxing and demuxing. Arrayed waveguides can provide you the 40 or 80 channels worth of mux demux. On the receive side, as mentioned before, you don't have the option to not include a filter on the receive side, so you need to use one of these two technologies that can isolate that receive channel.
Scott,
Yeah.
you said for these, you guys think, I suppose, going to electrical and then back to optical all the time, right?
In this case, yeah. So if you were to express through a terminal multiplexer, this is showing a single direction, but if there was another interface on that far end there, we'd be back in the electrical domain, regenerating an optical signal again before transmitting.
Yeah.
So
Yeah. Okay. Thanks.
no option to just express right through the node without converting back to electrical first. So as we talked about, like, there's some limitations in terms of how far you can go on a single fiber. And one of the inventions, I think this came up in the 80s, was the invention of optical amplifiers. The one that is typically used today are erbium doped fiber amplifiers, or EDFAs. What they allow you to do is receive a signal that's at a very low level, it's come in attenuated, pass it through this amplifier, and you'll come out on the other side with significant amount of gain. One drawback is it does add some noise to the signal. So it'll amplify any noise that exists on the signal coming in, plus it'll add some of its own, just like an electrical amplifier would add noise to the signal. So it has a noise figure. If you're familiar with RF, it's a very similar concept. These get deployed both with the MUX and DMUX components in some cases. So MUX and DMUX has some loss associated with it. You might want to transmit with higher powers. You could use an amplifier to increase the output power. Or if you're going a very long distance across the network and don't need to add drop, you can deploy these at intermediate locations and amplify the signal before you've completely lost your power levels. So the noise, this is an example here. We go node A to node D. This distance is too long to go straight through. It's more than the 23 dB link budget I mentioned earlier. So you can deploy these amplifiers. This is what it's showing at node B and node C. We wouldn't have any access to the signal if we wanted to add or drop the signal at those locations. But now we'll have enough power at node D to receive the signal we're trying to send. One of the drawbacks with the noise is it builds up as each time we amplify the signal, we're going to add more noise to it. The parameter that we'll actually measure is the optical signal noise ratio. So this diagram shows two optical signals. This is their peak power here. And down here in the gray is ASE. This is the noise. It's amplified spontaneous emissions that are caused by the amplifiers at those intermediate sites. So here what we measure is we measure the peak power of the signal versus the noise level integrated in it's typically a 0.1 nanometer resolution bandwidth. You measure the power levels and compare those two to determine optical signal noise ratio. Why that's important is because as you increase the amount of noise that's associated with these signals, the bit error rate increases. So you can see here, moving this direction, this is decreasing signal to noise ratio, and this is increasing bit error rate. So there is a limit to how many times you can amplify the signal in the network before you lose the fidelity. Okay, so with the terminal multiplexer, you didn't have the choice of expressing through a node. Optical add-drop multiplexers give you that option. In this case, we're looking at from node A to node D here. We have two signals that we want to pass all the way through. So at those two intermediate nodes, node B, node C, those are considered express signals. We're not going to touch them electrically. We'd like them to just pass through optically on their way to node D. But the last signal here, the green one, we need to access at node B. So we need to gain access to it, maybe process it electrically, pull some bandwidth out of the signal. The way this would be implemented is using single channel filters, which are thin film filters. Signal comes in here. This has all three signals inside of it. Thin film filter can drop a single channel and then have the other two continue on to the add filter. We can add the signal in here on the east side, which corresponds to this green signal going out. And then we could put an EDFA in line. Since we've already occurred some loss here, as you enter node B, there's some loss on those fibers between A and B. We could amplify the signal to get back to a good starting point to continue in the network. So this is an example of just how it goes together. So let me go back here for just a second. So this works fairly well. You have the option of expressing signals. You have the option of gaining access to them or dropping them, adding them back into the network. One of the drawbacks is since this only can access a single channel, if I want to add a second channel to this site, maybe I decide the red signal now needs to stop here for some reason. What I have to do is I actually have to break the fiber that goes between this add and drop filter and add another filter in between to gain access to that red signal. That means that everybody else that's running on this network is going to lose for some period of time, or at least incur a protection switch as we go the other way around the ring. This has to be done both on the drop side, has to be done on the add side, and it means that someone has to drive out to this node B, wherever it may be, and add those new components. So ROADMs came about. A ROADM is a reconfigurable OADM. So this is a way of minimizing the amount of effort it takes for a technician to go configure one of these network elements. So the way this works is when you come in from your receive side, you're going to first demultiplex all the channels. So you have access on one fiber per channel that's coming in on that receive interface. It's going to hit two switches that are just single pole, single throw switches. a VOA then will multiplex the signals on the far end. So with the switches in this position, where they're both pointing at each other, the drop switch and the add switch, the traffic that comes in, like this red signal, will just pass straight through the node. So the key is that you'd have one of these switches for each one of the signals that you'd be supporting. So if you had an 80-channel system, you'd have 80 of those switches in line. So, but if you throw the switch now, which you could potentially do through software, this is just a simple optical switch. Now the signal, instead of passing straight through, will come down to this drop and basically stop at that node. Same thing on the add side. Now you have access to add that back into the network, leaving the node. So it's less maintenance for the operators. They don't have to go to that site and add new components. It's all there from day one. So typical implementation today uses a device called a wavelength selective switch. These are usually based on either MEMS, which is micro electromechanical switches, or liquid crystal. This is what a node would look like altogether. The WSS really provides all those functions that we looked at in the last slide, but in a compact package. You get the ability to drop your signals, add signals back into the network, or express straight through the nodes using this technology. And this is how most ROADM networks are designed today.
And these are all done optically, you say?
This is all optical. So there's no electrical in this case at all. The only electrical interfaces would be behind this RX, so anything that you add or drop. But anything that you wanted to pass through, you can make that decision through software and provision that path. So a couple other impairments. We talked about noise. One of the other impairments that's really important in optical networks is dispersion. So there's two main types of dispersion that we're concerned with. Chromatic dispersion. I mean, this is the effect where as a signal goes through a fiber, different wavelengths are going to propagate at different velocities. And then polarization mode dispersion. There's two polarizations to an electromagnetic signal. So the two orthogonal polarizations of light have the potential to travel at different speeds. So focus on chromatic dispersion. It's probably the easier of the two to explain. So there are different fiber types that get used in networks. The most common is this SMF28. But the real difference between the different fiber types is their dispersion characteristics. So SMF28, you can see here what this curve is showing the rate of change of the velocity across wavelength. So this is the derivative of the velocity, propagation velocity. Out here at 1550 nanometers, where we usually run our WDM systems, there's about 16 picoseconds per nanometer per kilometer of dispersion. So the further you go in the fiber, the more dispersion you build up. And I'll show you what the effects of that is on the next slide here. So I have to talk about this in both the wavelength domain and the time domain. So to start off, this red line here says dispersion. This is really the velocity. So over wavelength, which is the x-axis, you have a variation in the velocity of the light that's traveling down the fiber. This here is your signal. If the signal was infinitely narrow, there would be no issue, because all your power is going to travel at the exact same velocity as it goes down the fiber, and there would be no issues with it. But when you modulate a signal, obviously it takes some amount of bandwidth to push information across the network. So you can see this curve. Some of this signal is going to travel slower than other portions of the signal. So this is in the wavelength domain. So this is your total power. Some of your power is going slower than others. And in the time domain, what you're trying to do, where the x-axis here is time, this is our binary 1 that we're trying to transmit on the fiber. Because this power propagates at different velocities in the fiber, it's going to cause some spreading of the signal. So you're basically going to spread that pulse that you tried to send down that fiber out in time domain. So here's an example. This is a simulation that we ran as an example. We took out all the other impairments you could have and just included dispersion. What this shows is a pulse stream. So this is just a series of ones and zeros in the optical domain that would be transmitted on a fiber. So this is at the very beginning of the fiber what the pulse looked like. And then I just have a couple of examples that show at different points along the fiber. First at 40 kilometers, you can see it's starting to have a little bit of distortion. 80 kilometers, it's building up. 120, you can see it's definitely changed the signal. This is just the dispersion impact of the fiber itself. It's kind of hard to tell what the impact of this would be, though. So typically we'll use an eye diagram to look at this. So this is that same signal, but overlaid on top of each other in a persistent manner. So this is a whole bunch of transitions triggered at one point, like you can think of this as an oscilloscope that's showing the optical power over time. And this is what it would look like at 0 kilometers. What we're interested in here when we're trying to make the decision of is the bit a 1 or a 0, first you have the slicing level, where below the line it's a 0, above the line it's a 1, and then you have the sampling point, where what's the ideal time along the x-axis to make that decision of is it a 1 or a 0. So you can see here now, as we go down the fiber, you can see a little better in this mode with the eye diagram the type of impact you get from dispersion. To this point where you get out to 120 kilometers, it might look here like these are the two places where you're trying to sample the data, but actually it's down there in the middle. So this might be your slicing level now. These are, anything down here is your zeros, anything above is your ones, and maybe you pick that as your sampling point. But obviously any other impairments here are going to make that decision even more difficult to make, and at this point you're probably already at the point where you're going to start receiving some errors. So we need to compensate for dispersion, or we're not going to be able to transmit the signal over these types of distances. And the way that's done is basically by putting another piece of fiber in the transport node that has the exact opposite characteristic of the fiber that exists in the network. So if this was our curve for SMF28, we build a specialty fiber that has the exact opposite characteristic and have to put that in line with the signal. So this will put the signal back to its starting point by just reversing the velocity of the signal across that band. There's more issues that we have to deal with optical. So nonlinearities, they're extremely difficult to deal with. They're difficult to simulate. There's several. There's 5 main types of nonlinear effects that we have to deal with in optical networks. Take a look at one of them. This is 4-wave mixing, first on the list there. So this is a picture from an optical spectrum analyzer. So this is a device that basically can sweep across different wavelengths and measure the power across wavelengths, just like an electrical spectrum analyzer would, but in the optical domain. So you can see here the x-axis is wavelength. This shows 8 different channels that are turned on. We're transmitting at 6 dBm on average per channel. And this is what we're going to input to a specific type of fiber. This fiber in particular is really bad for nonlinearities, and so you can see the effects pretty easily here. So that signal that we just had, we transmit it, deliver it to a fiber, measure with an optical spectrum analyzer at the other end of the fiber, and you can see there's all these new components that didn't exist in the signal that we put in the fiber. This is part of the nonlinearities. The different signals that are going into the fiber are mixing with each other and creating new components. So you can see here again, we had 8 signals. We watch this middle location here. All of a sudden there's a new signal that didn't exist before. The problem with this is that these signals also exist underneath these signals that are actually carrying the data that we're interested in, and it's causing interference and can lead to errors again. So it's another area in optical networks that we have to be concerned with. Yeah?
What kind of resolution bandwidth do you need for your optical spectrum analyzer?
So this one, let's see, what is this one set to right now? It should be up here on the screen. Typically, so we do most of the measurements in a 0.1 nanometer.
What?
But I believe like this sweep right here was probably taken in a 0.02 nanometer. Sorry, 0.02 nanometer resolution bandwidth for the sweep. But in terms of power measurements, we make the power measurements in a 0.1 nanometer resolution bandwidth. 0.1 nanometers is just a standard they use for OSNR calculations. So okay, so we have all these impairments that can build up and cause problems. The last resort really is OEO regeneration. So OEO is optical, electrical, optical. So we're going to bring in an optical signal, convert it back to the electrical domain, clean it up, and then transmit it again optically. So we can take that first component we talked about, the transponder, and instead of using a client transceiver that's a gray signal on this end, we can replace it with a DWDM transceiver. And so you can bring in this signal like the one we looked at in the dispersion plot that has a lot of distortion, run it through our processing, retransmit the signal as a clean waveform again. So now you can go further across the network.
So the dispersion, you use the electrical circuits to do take care of dispersion, basically to delay it a little bit more. Everything, part of it to match the whole thing, right? Yeah,
so there is a lot of advances in electronic dispersion compensation, where you can use DSP basically to compensate for a lot of these effects. Since these are linear effects, it's easy to compensate for them in DSP. As you get to higher bit rates, 40 gig and 100 gig, that's essential. All these impairments become worse and worse as you increase the bit rate. You have less margin for error at the higher speeds. So.
And the electronics can deal with such a speed. When you are making the digital processing thing, would you be able to handle such high frequency as well?
Yeah, I wasn't going to cover this, but maybe I can show you a quick example of, so 100 gigabit per second transceivers, what they've moved to is QPSK. So instead of having a straight NRZ modulator, we're actually doing phase modulation of the laser. So you have a laser that, in this case, at 100 gig, they're using 2 different polarizations of light and doing QPSK modulation on each polarization of the light and then combining them onto a single fiber. So each of these are running at 50 gigabits per second and then multiplexed to give you a total of 100 gigabits per second in a single wavelength band. But the key to this is a coherent receiver. So when the signal comes in at the receive side, first you split up those 2 polarizations of light with a polarization band splitter. Then you have mixers, just like you would in an RF receiver, and a tunable laser. So the tunable laser does the down conversion of the light. You have multiple receivers that feed into ADC. And I believe this ADC delivers data to the DSP at a rate of, I believe it's 8 terabits per second worth of data to process. And it's delivered to the DSP. It does phase estimation, equalization to account for dispersion. In 100 gig networks, where dispersion compensation is a big portion of the cost in a 10 gig network, it's almost not required in 100 gig networks because of the power of the DSP being deployed. So this is technology that's being worked on heavily today. Some initial trials have gone on, and in 2012 and 2013, we expect it to be more of a mainstream technology. So anything else? That was really all I had. Any other questions or? Yes.
I was just wondering, for the diagram for the ROADM that you showed, one of the practices that some companies are kind of starting is to put, rather than putting those drop switches that you showed, they have these splitters which essentially allows the signal to pass through at the same time you can drop it.
Yeah. So I'll show you the, go back to that one here. So while this was how ROADMs were initially built, this is pretty much not used today. This is more of a logical view of how a ROADM operates. So this is really how most ROADMs are implemented today. So when you come in on the receive side, you have some gain control because you're going to be going through a lot of processing. You're going to have loss, so you might need to boost the signal first before you enter into the guts of the ROADM. So you come in, the EDFA will actually handle passing that signal through the dispersion compensation, so that fiber that has the opposite characteristic. You come in, and this here is a splitter. So the splitter will broadcast all the signals that came in from the fiber over the express connection, and then also provide a copy of all the signals down here to an AWG. An AWG is a bulk demultiplexer, so you can demultiplex up to 80 channels in an AWG. And then your receiver gets hooked up to the port on the AWG where the channel that you're looking for exists. So you have a copy of all the signals coming down to the AWG and a copy coming across to the WSS. And what the WSS does now, you have signals coming from your transmitters multiplexed onto a fiber. So you basically have potentially up to 80 channels on each of these fibers going into the WSS. The WSS can then select which channels are going to be multiplexed onto its output side. So you can pick a channel from the express direction or pick a channel from the add direction. So you could even have one wavelength present on both of these and operate that switch to pick which of those two signals is going to be sent out the transmit port of the device. So this is the architecture that's used for most ROADM deployments today, based on WSS.
And then the micro-electro-optic type of things that you have are mainly at the splitters and also thinking, right, or what?
The microelectronic is mainly in the WSS. So those are mirrors that will focus the signals on the appropriate port. So in this case, this is a 3-port device. They make devices that go up to 24 ports. And so the different wavelengths get directed to the correct output port.
And then with these micro-electro-optic things, you will be able to, in fact, do the configuration, right, from remote, I suppose, right?
Yeah.
How quickly could these do these things?
This is in the range of milliseconds to reconfigure, so it's very quick. Most of the new WSS devices actually use liquid crystal, so they're demultiplexing the signal into spatially demultiplexing the different wavelengths, then having these hit a liquid crystal device where they write an image onto the liquid crystal device that directs the signals to the appropriate output ports. Yes.
Could you give an idea approximately what these components cost in a system?
EDFAs are in terms of components, the EDFAs are in the thousands of dollars. WSS as well.
Mm-hmm.
I'd say everything here, with the exception of maybe the smaller components, the BOAs, the splitters, EDFAs are in the $1,000, $2,000 range. WSS in that same ballpark. So these are big, expensive components. They're not chips. They're sub-assemblies. So these are a WSS is maybe a 5-inch by 7-inch box that includes all electromechanical components to allow the mux and demux. So the electrical interfaces are basically just for control in this case. Is there anything else?
I was just wondering if you know, like, for example, if you just have this express signal passing through and you don't necessarily need the add drop portion, which is primarily electrical,
Mm-hmm.
and if you turn it off and then turn it back on, how long do you think, or is there any like rough estimate as to how long does it take for it to reconfigure and go back to the way it was?
So if you shut this down, like power this down and turn it back
Just
on.
the electrical portion of it. So effectively what happens is that your splitter is basically whatever that's under that, which is just electrical portion of it, is turned off.
Yeah.
And then you turn it back on when you need it.
Yeah.
Is this possible?
In this case, the WSS requires power to be able to direct the signals to the appropriate output ports. Same with the EDFAs. The EDFAs will become will basically shut down if they're not powered. So these components typically all require power to operate. In terms of them coming back up, it's really a question of how quickly can the software boot and configure all the devices properly. So if it's been cold, because we're dealing with wavelengths and in terms of nanometers, a lot of these devices are thermally controlled. And so from a cold start, if the box has been sitting powered down for a while and you turn it on, there is typically some startup time required to thermally stabilize all the devices to get the right performance out of them. So any change in dimensions based on change in thermal conditions can cause a degradation in performance.
The only reason I ask this question is because one of the main portions of this system that's actually very energy hungry is the electrical portion of it. And there are a lot of ideas that by turning off certain portion of it, especially when you have static traffic, you can save a lot of power. And so people just kind of randomly suggest you can turn off this portion and that portion.
Yeah, and power consumption in these networks are extremely important, especially in data centers where power is one of the biggest costs, higher than any cost of buying the equipment and deploying it. And it's like the cost of the power is significant. So.
Yeah, so at each node, in fact, in the big diagram that you showed us, initially that you have all of these nodes across the region.
Mm-hmm.
So you have at least a couple of these things there then, right, in each node then, right?
Yeah. Typically a WSS module would handle a single interface. So with a lot of these drawings, and I didn't mention this before, this is showing a single direction.
Right.
But this would actually be two modules. So this line down the middle, this would be your west card, and this would be your east card. But your west card also has this portion, just mirror image up on the top side. So you can take this whole image, mirror it, and flip it back up there, and you have a receive direction and a transmit direction on each of the cards.
Right. And then if you wanted to configure these things from remote, in fact, the other day you showed us, you had a software, you could go to each of these nodes and so forth and look at it. So basically, all of these things are connected to the internet somehow with some electrical, circuitry to be able to do all of those things, right?
Yeah, I don't think it's shown in this picture here, but one of the things that all of the devices we build has is something called an optical supervisory channel.
Yes.
And what it does is it just goes between nodes in the network, and it's a 100 meg Ethernet channel, so it's a fast Ethernet interface that runs outside of the band of the DWDM.
Right.
So we use 1510 nanometers, and so all of these have a connection at 100 megabits per second, so that all the configuration information and communications can run over that channel out of band and not affect any of the traffic that's flowing.
Right, that's what I was looking at, trying to ask you. So basically here you have then the supervisory channel to help you do the configuration out of band.
Yeah, so we can communicate between all the nodes and coordinate any type of power balancing that needs to go on or provisioning changes using that supervisory channel.
Yeah, thanks. Okay, are there any other questions? I should say that I really enjoyed the talk and I learned a lot out of it, and I hope that you all did. So let's thank Scott for giving us such a